In this video, I'm going to explain the application of Laplace equation to a coaxial cable. So we know that coaxial cable is having two concentric cylinders separated by a dielectric medium. So basically, coaxial cable is a concentric cylindrical system. One of the cylinders is charged, other one is grounded, generally. They can also be maintained at different potentials to produce electric field between the two cylinders. Now, I'm going to explain how to use Laplace equation to find this potential distribution. And from this potential distribution, we can also find the electric field distribution. So for that, I have taken two problem statements here. The first one is to derive expression for capacitance per unit length for a coaxial cable using Laplace equation. And in our previous discussion of parallel plate capacitor, we have seen that Laplace equation helps to find potential distribution in an electrical system. From this potential distribution, we can find electric field distribution. And from electric field, we can find flux density. From there, we can find surface charge density producing the flux density. So by integrating ρs, we can find total charge on the conducting cylinder. From Q, we can find the capacitance. So this is the sequence of the derivation. So first, we have to find V, the potential distribution from the Laplace equation. So if you see the second problem statement, there it is required to find potential at a point in an infinitely long coaxial cable. Coaxial cable is generally assumed an infinitely long line charge. It is similar to a line charge with inner radius A, outer radius B. In the second problem statement, the radii are given. In the first statement, nothing is mentioned. We can assume the radii accordingly. So with this information, we shall proceed to the problem. So we have here a concentric cylindrical system, which can be taken as a coaxial cable. So the distance measured from the axis is the radius. The radius of the inner cylinder is A and the outer cylinder B. This is what is given in the second problem. And then nothing is mentioned about the boundary conditions of the coaxial cable. That means no potential levels are mentioned for inner and outer cylinders of the system. Therefore, we shall assume the appropriate boundary conditions for this particular system. I mean, let us ground one of the cylinders for proper functioning of the cable. Then the potential on grounded cylinder becomes zero. Any one of the cylinders can be grounded according to the requirement. If outer cylinder is grounded, then inner cylinder can have a potential value, say V0. V0 is any constant voltage at the inner cylinder. Now, the potential difference, let us say Vd, between the two cylinders is V0 minus 0 V0. So V0 is the potential difference, but we want here potential distribution between the two cylinders. That is the space between the two cylinders, which is a dielectric medium, will have the potential distribution, which can be obtained from the Laplace equation. So here we have one more diagram, which is the cross section of the coaxial cable. This is for better understanding of the system. So same values I would like to transfer for this diagram also. It is easy to understand and write also. So V is going to be 0. Inner cylinder, V is equal to V naught. Radius of the inner cylinder is A and the outer one is B. These are the boundary conditions given in the problem. First boundary condition, V equal to 0 when radius equal to B. Second boundary condition, V equal to some value V naught when the radius is A. So these boundary conditions are required to find V using Laplace equation. Now let us start with the Laplace equation. That is del square V equal to 0. So the Laplace equation is given by del square V equal to 0. The del square V can be expanded in terms of the three variables of the coordinate system. Coaxial cable and concentric cylindrical system are well explained in cylindrical coordinate system. So we shall expand del square V using the expression 1 by rho, dou by dou rho into rho dou V by dou rho plus 1 by rho square, dou square V by dou phi square plus dou square V by dou Z square. So we know that Laplace equation is having three partial derivatives. Here rho is the radius in cylindrical coordinate system. So from the boundary conditions, we can conclude that potential V varies only with respect to the radius rho. So the potential do not vary with respect to the angle phi and Z. That's why these two terms are not needed. So we have only the first term, that is 1 by rho d by d rho of rho into dv by d rho is equal to 0. This is what is left now, after omitting the second and third term. So in the first equation, we used the partial derivatives, and in the second equation, partial derivatives are removed. We use d by d rho because to tell that the potential V varies only with respect to one variable. Partial derivatives are used when the variables are more than one. Now, we would like to find this V. So we have to take out this V from this equation. So we shall start eliminating one by one terms from the left-hand side. So we shall send this rho to the right side so that it becomes rho into 0 is 0. So we are left with differentiation of rho into dv by d rho is equal to 0. To remove the differentiation, we shall integrate with respect to rho on both the sides. Then we get rho dv by d rho. So integration with respect to rho cancels differentiation with respect to rho. On the right hand side, integration of 0 is 0 plus we introduce a constant of integration, let us say C1. C1 is any arbitrary constant. So these constants are defined, these constants are used to define the boundary conditions. Next, we shall put the rho to the right side so that we can find V. Now, the RHS becomes C1 by rho. We shall go for one more integration to remove the differentiation. So we get directly V. On the right hand side, C1 is constant. Integration of 1 by rho with respect to rho is natural logarithm of rho plus constant of integration is C2. C1 and C2 are two arbitrary constants which can be found by the boundary conditions, whatever we mentioned in the beginning. So this is the equation giving us some idea of potential distribution in a coaxial cable. So V is a function of rho, the radial distance. So in a cylinder, the radial distance is a distance measured from the axis of the cylinder. So potential varies logarithmically with respect to radial distance of the cylinder. Now let us find C1 and C2. To find C1 and C2 from the boundary conditions. So boundary conditions are usually mentioned in the problem itself. If not, they can be assumed appropriately. Okay. So now first boundary condition, as I said, one of the cylinders is generally grounded. So V is equal to 0. At which cylinder is grounded? The outer one, whose radius is B. Therefore, the radius is B for outer cylinder. This is the first boundary condition. We shall apply this condition to equation number 1. Therefore, equation 1 becomes V equal to 0, find LHS is 0, C1 logarithm of the radius of zero potential is B plus C2. So from this equation, I can write that C2 is equal to minus C1 log B. Here B is known, it's a constant given in the problem itself. So log B is another constant. C1 is one more constant, but C1 is still not known. So to find the C1, I'm going to use one more boundary conditions. Then I will come back to this equation to find C2 again. The second boundary condition is the potential V0 maintained at inner cylinder of radius A. So rho radius, when rho the radius becomes A, the potential is to be taken as V0. So therefore here once again we shall put this boundary condition to equation 1 to get, okay, equation 1, V becomes V0, fine. C1 is constant, log of radius. What is the radius for V0? It is A plus C2. For C2, we have one relation already in the previous step. So we shall make use of it here. V0 is equal to C1 log of A plus C2. In place of C2, we write minus C1 log of B. So this equation comes from here. So now C1 can be taken out as a common factor. This becomes log A minus log B, which can also be written as log of A by B. Therefore, C1 finally becomes V0 divided by log of A by B. So V0, A and B are the values available from the given boundary condition. So all of them are known. That's why C1 is completely found. Since C1 is completely found, we can go for C2. Which is given by minus C1 log B. So we shall replace C1 by V naught log of A by B into log B. This is the C2 now completely. So C1 and C2 are calculated from the given boundary conditions. So we can put this C1, C2 back to the equation 1. That is the Laplace equation we found. So the values of C1 and C2 are used in equation 1. That is, the equation 1 was C1 log of rho plus C2. Here, the C1 becomes V naught divided by log of A by B. So V naught divided by log of A by B is C1 into log rho plus C2 becomes V naught log of A by B into log B. So C1 and C2 are introduced into the equation 1. We can simplify it further to get a proper statement for V. These two terms are common. So V naught by natural logarithm of A by B into log rho minus log B. Finally, log rho minus log B can be written as log of rho by B. So this is the final expression for potential distribution in a coaxial cable. Equation 2. So here V naught, A, B are constants. So only variable is rho. So the potential is a function of the radial distance in a coaxial cable. Now to find electric field distribution from the potential distribution, we can proceed in this way to find E. So what is E? Electric field distribution. The electric field distribution E can be found from V using the relation of gradient. E is equal to minus del V. For a cylindrical coordinate system, the gradient of potential is given by dou V by dou rho A rho minus 1 by rho dou V by dou phi A phi minus dou V by dou Z AZ. This minus comes from the negative gradient. But from equation 2, we can conclude that V is a function of rho only. V does not vary with respect to phi, so differentiation 0, does not vary with respect to Z, so differentiation 0. So we can go further with this relation. So electric field is given by the differentiation of electric potential with respect to radial distance. So the dimension of electric field is volts per meter, dV, change in potential, to d rho, change in distance. So now we shall differentiate V with respect to rho. So d by d rho of, we shall substitute for v from equation 2. From equation 2, v is given by v naught by log of a by v, log of rho by b. So this relation is taken from equation 2. The second logarithm contains rho. The first term is constant, so v naught by log of a by b is constant. And then we have to differentiate. Only log of rho by b. This log of rho by b, I would like to expand as log rho minus log b. So that helps to make the differentiation simple for you. So in the next step, it's a simple differentiation with respect to rho minus v naught log of a by b. Differentiation of log rho is 1 by rho. Differentiation of log b is 0 because there is no rho in the second term. So that goes to 0 after differentiation. So a cap rho. This is the expression for electric field distribution in a coaxial cable. We can observe a few points here at this point of time. First one, the direction of electric field is negative a cap rho. That means the unit vector is negative radial direction. But actually, if you carefully observe, the log of a by b is a negative number because a is less than b. A is the radius of the inner cylinder and b is the outer. So the ratio a by b is less than 1. So the logarithm becomes negative. So minus to minus plus, even though the minus is present in the equation, but actually it doesn't exist in actual equation if you mathematically calculate it. So therefore, to give more scope for this expression, I would like to take minus sign for this logarithmic and would like to write this as log of b by a. So minus sign can be used to interchange a and b in the ratio so that it becomes a cap rho. So now this is completely meaningful. So the direction of the electric field is radial. We know that one from the module 1 itself. Second one, electric field is inversely proportional to 1 by rho. We know that electric field is inversely proportional to the radial distance in an infinite line charge. So therefore, the coaxial cable or the concentric cylindrical system behaves like an infinite line charge. That is very important. And at the same time, I would like to draw the cylindrical system to show the direction of electric field. This is here. See now, the electric field is projected in the direction of a cap rho. So it is easily explained in the cross-sectional diagram. The field is distributed between the two cylinders. Inside the inner cylinder, there is no field because inside the inner cylinder is a conducting medium. Field does not exist inside a conducting medium. It's always 0 here. Field is 0 here and it is not 0 between the two cylinders. And this is projected in all the directions, that is radial direction. And electric field is perpendicular to the surface of the inner cylinder at every point. So these informations are very useful in understanding the behavior of electric field in cylindrical system. Once we find electrical distribution, we can easily find flux density vector here. That is, let us find D. So we know that D is related to E in terms of the permittivity of the medium. Therefore, D is equal to epsilon naught V naught log of B by A to 1 by rho A cap rho. Here I have assumed the medium as air medium between the two cylinders just for mathematical interpretation. Once D is found, we can go for calculation of surface charge density. Surface charge density in coulomb per meter square. Carefully observe that the dimension of rho s and dimension of D both are same. Both of them are coulomb per meter square. And you can recall the concept of boundary conditions between a conducting medium and an insulating medium, that is dielectric medium. That means if there is a boundary between an insulator and a conductor, then you can find the charges residing on the surface of the conductor. As I said already, inside the conductor, no charge exists, no field is developed. The charge exists only on the surface of the conductive medium. From this charge, electric field is produced within the dielectric medium. So the electric field in the dielectric medium is because of the surface charge, and it is always perpendicular to the metallic surface or conducting surface. So the direction of electric field is always perpendicular to conducting surface holding the surface charge rho s. Concept number 1. The magnitude of this electric field is given by the relation of electric flux density D, because the electric flux density D is also perpendicular to the conducting surface. Directions of D and E are same. And also from the boundary conditions of this conducting and dielectric medium, we can write this relation rho s is equal to modulus of D. This can be proved. This can be proved and is available in the literature. You can refer for more information. That means the scalar quantity rho s, surface charge density, is given by the modulus of electric flux density. And electric flux density is always normal to conducting surface. So we can also write that rho s is equal to dn. N stands for the normal component of D. So from the rho s we can find D. From the D we can find E. So whenever you want to find the magnitude of electric field near the surface of a conducting medium, we can use this relation. So in this derivation, we can find rho s from the D, and D is already available. So modulus of epsilon naught V naught divided by log of B by A 1 by rho A cap rho. So copied the complete equations of D here. And we know that D is a function of rho, because electric field is a function of rho. So electric field and electric flux density is distributed throughout the dielectric medium. So rho is the distance of the point of your interest. But when it comes to surface charge, surface charge is existing only at the surface of the conductor. It does not exist anywhere in the dielectric medium. That's why when finding rho s, we have to put the radial value as A. This is because in the coaxial cable, only inner conductor is under charge, positive charge, let us assume. As we all know that outer conductor is grounded, that is negative, grounded. Inner conductor is charged. The charge density on the inner cylinder or cylindrical conductor is rho s. So you cannot find any surface charge density between the two cylinders. That's why we have to put the radial value as A while finding the rho s. So from this discussion, we can get the rho s value as epsilon naught V naught log of B by A. 1 by rho becomes 1 by A. The modulus of unit vector is 1. That's the magnitude of unit vector is 1. Coulomb per meter square. We can observe that rho s is a constant here. Epsilon naught, V naught, B, A, everything is given in the problem statement. So it's a constant value. Once we find the charge density on the surface of the inner cylinder, we can also find the total charge. Total charge on the inner cylinder. Inner cylinder. In this case, it's only inner cylinder because the outer one is grounded, so not needed. We know that the total charge is given by surface integral of rho s. But from the previous step, we can conclude that rho s is constant. So the surface integral is only for ds. So it gives finally rho s into total surface area of the inner cylinder. Total surface area, because integration of ds is s. That is the total surface area where rho s is present. Total surface area of inner cylinder. Inner cylinder is a cylinder of radius A. Next, to find Q, we shall substitute for OS, that is epsilon naught V naught log of B by A into 1 by A. This is the charge density and area. Surface area of the inner cylinder. Cylindrical surface area is given by 2 pi RL. R means radius. In this case, radius is A for the inner cylinder. So 2 pi L, where L is the length of the cable. Length of inner cylinder or length of the cable itself. So now we can write Q as here A and A cancelled. So 2 pi epsilon naught L into V naught divided by log of B by A. So this gives total charge accumulated on inner cylinder in coulombs. Finally, the capacitance as asked in the problem statement of first one, capacitance C of the coaxial cable. Of the coaxial cable is given by C is equal to, we know that capacitance is given by charge into Vd, where Q is the charge stored. on the cylinder. It is the potential difference, not the distribution. To be careful here. It is the potential difference between the two cylinders. So as I said in the very beginning itself, charge told is Q. Potential difference is V0 minus 0. One of the cylinders is the potential. So Q by V0. So therefore, C becomes now. So in place of Q, we can use the value we derived in the previous step, that is 2 pi epsilon naught L V0 divided by log of B by A. This is Q. And the potential difference is 1 by V0. You can see that V0 is cancelled. So finally, the capacitance becomes 2 pi epsilon naught L divided by log of B by A. In farads. But here, one term to be observed carefully, that is L. L is the length of the coaxial cable, which is quite long always. So we would like to remove L from our discussion. So we shall divide by L on both sides. Then we get capacitance per unit length. Unit length is C is equal to 2 pi epsilon naught divided by log of B by A. So this capacitance is different from the previous one, and this is in farads per meter. Be careful, it's in farads per meter. If you want, you can call it C dash just for discrimination. So this is the complete derivation, which explains you how to find capacitance using Laplace equation in concentric cylindrical system. Thank you.